Good afternoon. Our group's focus is composite impurity tensile testing. We have Catherine Germain, a junior student for mechanical engineering, Brandon Cloutier, a senior mechanical engineering student, Caleb Rathbun, a senior mechanical engineering student, Shane Carter, a senior mechanical engineering student, and Liam Costello, a senior mechanical engineering student.
With this project, we tested to see how foreign object debris, or FOD, within the composite resin matrix affects the tensile properties of composites. This is to answer the question, does adding a small amount of FOD actually strengthen the composite? This is plausible because particulate reinforced composites tend to prevent dislocations in the composite microstructure. Hybrid fiber particulate reinforced composites are common in the aerospace industry, but will FOD particles have the same effects? This is significant because if so, manufacturers would be able to increase the ISO classes of their cleanrooms, decreasing manufacturing cost. However, if FOD always decreases strength, then a tolerance can be placed on the allowable amount of FOD in the composite, increasing quality and safety standards of the manufacturing process. To get this data, a dog bone tensile test is performed using fiberglass samples with varying percentages by mass of polyester particulate, or glitter. Our test is innovative since it can be done on a small, inexpensive scale. Prior to the experiment, we conducted a literary search on how FOD affects composite strength and the current preventative measures being taken. With this, we wanted to explain how prevalent composites are in industry and how drastically FOD can affect the safety and integrity of the piece. To begin, we'll talk of the damage to the fiber. Fibers are the primary means of withstanding load in a composite. Damaging the fibers causes a weakening in the composite's integrity and sublayer delamination in the form of yarn bending and fracture. As for the matrix, depending on FOD shape, the matrix can be heavily damaged, causing crack propagation. This decreases the protection on the composite fibers and can lead to complete structural failure. Failures like this cause accidents such as the 2018 crash of a Boeing 737. This had a composite fan blade break and destroyed the internals of the engine mid-flight along with the depressurization of the fuselage. This led to the death of a passenger. Composites are extremely prevalent in industry, as shown by the construction of the Boeing 787, which is 50% composite material by weight. To prevent FOD in the clean rooms, currently layup rooms prevent FOD by being classified as a certain ISO class. These classes range from 1 to 8, where 1 has 10 particles per cubic meter and 8 has 100,000 particles per cubic meter. Our test intends to further quantify the necessary ISO classes needed for certain composite part manufacturing. Before testing, we had to manufacture our composite samples. As shown in the first image, 12 layers of 9x4 inch 90-degree aligned fiberglass fabric were cut per sheet. Then epoxy was mixed with 2-hour hardener for 3 minutes. This was then put under vacuum to remove bubbles and prevent voids between the fiberglass layers. This resin was then separated into 4 containers, each containing various percentages of glitter. These 4 sheets were then laid up by saturating each layer in their respective FOD percentage resin mixture. The percentages were 0, 5, 10, and 15% glitter by weight. The final laid up sheets are shown in the second image. After this, the composites are bagged up and attached to vacuum. This is shown in the third image, and the sheets were left under vacuum for 24 hours to cure. After 2 additional days to cure out of vacuum, the sheets could be water jet cut. Each sheet provided 12 dog bones, and an initial cut line was added to prevent delamination. Our final dog bones are shown in the last image.
According to the background research, adding FOD should cause a significant decrease in the structural integrity of the compost. This is because additional particulates cause voids and pockets between the fiber layers. This then causes stress concentrations, which under load will cause the composite to fail. However, particulates can also increase strength by enhancing the matrix strength and properties, decreasing dislocations. Our predictions were that 5% FOD would be the strongest of any sample, followed by 0%, 10%, and then 15%. Our results were as follow. 0% broke at 325 pounds, 5% broke at 347.5 pounds, 10% broke at 360 pounds, and 15% broke at an average of 352.5 pounds.
Here are some of our testing considerations. First, we have our dependent variables, one of which is the elastic modulus. This is dependent since it is a value determined by the amount of FOD present in the sample. Stroke length, strain, and stress are also dependent variables since their values are determined by the force value applied. Some independent variables include the amount of force applied. This is because it is directly manipulated by the experimenter. The initial value of force begins at 200 pounds and incrementally increases 10 pounds until the point of sample failure. Also, the amount of FOD is an independent variable. This is because it is controlled by the experimenter when manufacturing. Some of our controls include the 0% FOD sample. This is because data following the samples containing FOD will then be compared to the original 0% sample. This will show how FOD affects the strength compared to a pure sample. Also, the manufacturing of each sheet is controlled since all sheets are manufactured in the same method and have the same cure time. A parameter is a value that is crucial to the outcome of the experiment, though it is not deliberately manipulated. This experiment has environmental conditions as a parameter since they need to remain the same for the experiment to have consistent results. Cross-sectional area and gauge length of the dog bones must also remain consistent for the experiment, and these are not deliberately manipulated since they are standard sizes.
For the samples, we used the dog bones we used in 201 as a reference to create dog bones in SolidWorks. The gauge length was recorded at 0.45 inches with a cross-sectional area of 0.1 inches.
Manufacturing and testing equipment. During manufacturing, a U-line balance scale with a resolution of plus or minus 0.01 grams was used to measure the weight percentage of FOD in the dog bones. A Stanley 12-inch tape measure with a resolution of plus or minus 1/32 inch was used to measure the size of the fiberglass sheets. A vacuum chamber pump and a 1/4 rocking piston vacuum pump will also be used during the manufacturing process. During the testing, the Model 1K Universal Tensile Testing Machine was used to test the ultimate tensile strength of the dog bones.
Here is our test plan. Step 1 is to set up the Model 1K Universal Tensile Testing Machine for testing and remove the clamp fixtures. This machine can break samples up to 1,000 pounds, which is sufficient for our test. Step 2 is to install the test sample into the clamps and reinsert the clamps into the tester. The samples must be thoroughly tightened into the clamps to prevent slippage of the sample. A vise is helpful to ensure a tight fit. Step 3 is to ensure the tester is reading 0 load and 0 stroke length. Step 4 is to apply 200 pounds of load to the sample and record the stroke length. 200 pounds is well below the predicted breaking point, so it would be a reasonable starting point for the data. Step 5 is then to increase the load up to the point of breaking in 10-pound increments, recording the stroke length at each additional 10 pounds. An Excel sheet detailing all the data is helpful to ensure easy data recording and analysis afterwards. Step 6 is to record the final load required to break the sample as a sample failure. It is pivotal to ensure these points show reasonable data since many factors in the manufacturing process could lead to premature breakage. Step 7 is to repeat steps 2 through 6 4 times per sample. Step 8 is to repeat the test for all 4 samples containing 0, 5, 10, and 15% FOD. Step 9 is to plot the stress-strain curves for each FOD percentage. Stress is calculated by dividing force by cross-sectional area. Strain is calculated by dividing stroke length by gauge length. Step 10 is to calculate and compare the modulus of elasticity of each sample to determine the strongest sample. This concludes the test.
For our risk assessment and safety measures, we had 3 things that we focused on that were part of our project. And number 1 thing was the resin fumes from the resin. We just counterbalance this to be safe by wearing respiratory masks and gloves and safety glasses, and we had nothing to worry about with those items on. And then the tensile tester, we just used the normal lab safety equipment like glasses and gloves, and just make sure while it was running that no part of our body or anything were by the tester, so if something broke or if it didn't work right, we didn't have to worry about it. And then the last thing was the water jet cutter, which we actually didn't have to do ourselves. We sent it to the lab, but the safety steps taken for that would just be wearing safety glasses and gloves and all the proper safety equipment, and just making sure that we wouldn't put any body part under it while it's running, because it would cause harm, and just be safe about it and stay away from it while it's running until it completed the job. For our overall process flow chart, we obviously made a design. We dimensioned that design so it would fit in the tensile tester that we could use in the lab, and we put it on a CAD model so all the dimensions were right. But then we could send that file to the shop, and they could water jet our samples, and they water jetted. There's 4 different samples. They had a percentage of 0% FOD, 2% FOD, 5% FOD, and 7% FOD, and we got 10 different dog bones from each sample. And after we got our samples, we tested 4 different samples from each percentage of FOD, and we went in increments of 10 from 200 pounds up to get our data. Some of our data was hard to tell the results, and then others was really close, and then we could put all that data together to come up with our final result of if FOD affected the strength of what we were going for, and we actually got pretty good data to show us that.
All right, so obviously, as you can see here, we have the slide that shows the results for all of the trials and each of the FOD percentages. And we had 4 trials, as we mentioned before, and so there's the 4 trials on each graph. And so we did stress strain curves to show the relation for 0% FOD, 5% FOD, 10% FOD, and 15% FOD. Obviously, as you can see, the 5% FOD was completely different than the others. That was our first trial, and we'll talk about that more in the error section. But other than that, we had pretty consistent data for the others. And so what we did, we took the data, plotted it out on a Google Sheet, and then created a graph, and we calculated the equation using their equation generator, and that gave us the average modulus for it. So for 0%, we had an average modulus of 416,538. 5%, which was the big error one, that was 134,646. 10% was similar to 0%, which was 465,251, and 15% following the others was 428,689. And so we concluded that from the results of the data that 10% FOD exhibited the highest average modulus of elasticity. This figure displays our initial team Gantt chart. Our progress followed a slightly different path due to safety training and material acquisition delays. 2 members of our team required respirator fit testing, which could not fully be completed on our timeline due to a lack of response from members of the EHS department. Also, manufacturing of the samples was pushed back to the end of March since our material could not arrive on time. This required the use of material already found in the composite lab, which slightly shifted the goals of our team. We initially wanted to manufacture 90 and 45 degree fiber direction samples, but we really had to shift to only 90 degree.
Budget. For our budget, we required 2 respirators and 4 organic vapor acid gas cartridges. The reason we needed these respirators and cartridges was during the fabrication process. Once the hardener and epoxy are mixed, harmful gases are released that requires the use of the respirator. The experimentation that we conducted from this course did not produce the results that we had hypothesized. It was expected from prior research that an increase in FOD would increase residual stress within the dog bones, resulting in a lower failure in the specimen. But from experimentation, we found that introducing FOD actually increased the ultimate tensile strength within the 10% FOD. Further experimentation should be conducted with a different FOD material closer to that of what you could find in industry in such as rocketry or other applications.